When I got into the solar industry in 2008, there was no solar design software on the market. And so we had to use the good old pencil and paper method for designing solar arrays. And that would often result in a sales rep going out to site, getting up on the roof, and performing a very detailed roof sketch for shade analysis. But we also talked about in the intro to solar program is now there's a variety of system designs that you can do to mitigate shade, whether it's a string inverter with multiple power point tracking, so it can track. It used to be the inverters only had one power point tracking. So if you had 5 or 6 circuits on the solar array, you would combine them into one circuit before landing on the inverter, and the inverter would just track the power out point of a system. And that would be problematic because a little bit of shade would mess up the power point tracking, confuse the inverter, and it would curtail its output rather substantially. So on a partly cloudy day, or if you had a little bit of shade on your solar array, that would wreak havoc on solar production. Nowadays, that design process does not need to be so exact, because if you know that you're going to be in a rooftop that has partial shade conditions, you could specify DC optimizers on every other module, or microinverters on every module, and that would make every solar module on the rooftop their own individual system, so that the shaded modules would no longer drag down the unshaded modules. Or if you're just getting a tiny amount of shade from the early morning or late evening, something that's not on your array, for the middle part of the day when the array is most productive, nowadays a string inverter with multiple power point tracking would be quite sufficient. But we need to start out with shade analysis and saying, well, how can we do some shade modeling using the good old-fashioned pencil and paper method without getting into commercial design software? Well, that's kind of a misnomer, because even when you're not using commercially available solar design software, you're still going to use kind of free online software resources to help guide your array. So doing solar design using pure pencil and paper method, we'll talk about what you can do, but even back in 2008, you weren't doing the whole thing by hand. Now, Google Earth is a free software, and it's very useful for solar design. So here we have a screenshot of Google Earth, and we'll pull it up in a minute, but there's a few things that I want to point out here. The first is that you get this date stamp, that the date of the Google Earth photo, when it was taken. And then there's this ruler tool on Google Earth that you can use to get you click on one point of the map and another point of the map. And so what we're doing here is measuring out the length of the shadow that this tree casts. And we see that this is a 80-foot shadow and this is important too, you get the bearing or heading or azimuth angle of the shadow. And at 160 degrees, what this azimuth angle means is that it's 20 degrees off of due south to the east. 180 degrees would be due south, 200 degrees would be 20 degrees off towards the west instead of towards the east. So what's interesting about this is we know the length of the shadow, we know the date that the photo was taken, we know the azimuth angle of the sun because it's casting that shadow. And so what we don't know is the angle of elevation to the sun. And so for that, and we'll get to that in a moment. We also have looked at PV watts in our intro class, and we'll go into it a little bit further today. But also as a reminder, if you want something a little bit more robust than PV watts, but you're not quite ready to go into commercial design software, like if you're doing your own project and you really you want to learn the concepts and you don't want to just use the assumptions that PV watts makes. Whenever PV watts makes assumptions that you can't hard code into PV watts, it's erring on the side of being conservative. So for example, temperature degradation. With PV Watts, you can't open up the module spec sheet and hard program the temperature coefficients. It assumes a temperature degradation that's actually about 15% too aggressive compared to the standard module types. And it's not like that's completely unflexible. Within the PV Watts input, you can select between a standard module and a premium module and a thin film module. And if you read the documentation, that's toggling those temperature coefficients. So you can kind of pick the best fit within PV Watts. But whereas with a system advisor model, you can actually hard code all of those numbers. Now, is that useful in preliminary design? Well, for residential, you're generally wanting to present a conservative production to your client. It's better to make the project work under conservative consumptions. It's better to undersell and over-deliver versus the other way around. Now, when you get into commercial software, assuming a 3 or 4% margin of error is not sufficient for getting project financing. The bank is going to want to see a precise estimate. And often that precise estimate means that you're actually presenting an array that is more productive than what you would present perhaps to your client, because the bank is wanting to be exact and you're putting in exact numbers, and instead of having that gray area in PV Watts where we're being conservative, commercial design software is more precise. And so by the time you get into the point of needing, say, the system advisor model for precision purposes, you're probably working in the solar industry or working with someone in the solar industry who has access to more precise modeling software. But PV Watts has a lot of hidden value in it that installers kind of gloss over, because a lot of installers, they're just looking for the annual production out of the system. And if you have net metering where you get retail value for whatever you push onto the grid, assuming that you're buying it back a little bit later, that net metering policy allows you to get the full value of the annual production out of the system. As net metering subsides, we have to consider, am I producing surplus at the end of the month? Am I producing surplus, throughout the day? That might play an impact on solar economics. But from the idea of remote site assessment, don't forget that PV Watts has this hourly download option at the end. So once you get your PV Watts estimate, you can download the results broken out on an hour by hour basis. And what you can see in this graph is for every hour of the day, for every day of the year, you can see what the power point of your solar array is. And so if you're saying, well, what should be the parameters of my shade analysis so that I don't get any shade on the solar array? Well, here we're examining our production in the winter time, pretty close to winter solstice. And out of this 1,000 watt array, we can see at 7 a.m. and 8 a.m., our array only gets up to about 7% of its rated capacity, whereas at 9 a.m., we've jumped up to 40%. And so really your most productive times in the winter are from, say, 9 a.m. To about 2:30, or from about 9 a.m. to about 3 p.m. And anything before then or anything after then is hey, you could pick that production up on a completely unshaded array. But generally in the very early morning and the very late evening, shadows get very, very long. And so it might be that the house next to you, or the tree that doesn't go up above the roof but is kind of level with your solar array, at those times it may be that the sun is so low in the sky that that we just simply ignore these tail end numbers that are a little bit small, because you could have that. Even if your array has no shade on it, it could be that the shadows have gotten so long that power isn't really ever going to make it out of the system. And so we see that in the winter time from PV Watts, you're looking at, something that's between 9 a.m. and 3 p.m. I apologize for my chicken scratch. And so you can do this by going and exploring, say, summer solstice and winter solstice, and you can determine what times of day your array turns on in the morning and off in the evening. In the summertime, solar arrays have a much longer period of operation, and the solar array may be lasting from like 7 a.m. to 5 p.m. Or maybe even 6 p.m. depending on your location and daylight savings time and stuff like that. And so we have a much longer solar window in the summertime than we do in the wintertime. And for that matter, shadows do not just go south. I mean, in the summertime in the morning, the sun rises in the north part of the sky and sets in the north part of the sky. So shadows can actually move south as well as north, even though you're in the northern hemisphere. And so it's always good to examine, say, if you're doing things by pencil and paper, saying, well, what is my shade condition at the extremes? So at winter solstice, what does my shade look like? At summer solstice, what does my shade look like? And even spring equinox and fall equinox. And also not just what the shade looks like at high noon, but at the start of your significant production. I mean, you don't want shadows on your solar array at 9 a.m. And in a ground mount array, that might be row to row shadowing. And so, you can start kind of defining what is my PV watts window, or what is my solar window based off PV watts. And so then it comes back to, well, in order to figure out where the shadows go, I need to know where the sun is on winter solstice and summer solstice and spring equinox and fall equinox. And also to calculate the height of this tree, I need to know where the sun is on the date that the photo was taken, 2012 or so. And so for that, we go online and we find what's called a sun angle azimuth chart. The U.S. Navy office puts out a really good sun angle azimuth chart. If you just go to Google and Google sun angle azimuth, it's going to be one of the first ones that pop up. But you put in your city and you put in the date that you want to explore. So here we're exploring winter solstice, and it'll give you a breakout of where the sun is every single day on winter solstice. And if we know the length of the shadow, we know the height of the object. If we know the azimuth of the sun, we know what direction that shadow is hanging off on. So, what we're going to do here is go on to Google, and we're going to Google sun angle azimuth chart. And here we are on our table. Now this photo on Google Earth, this was taken at November 24th, 2012. So we go to our sun angle azimuth chart and we put in, November, I already forgot what it was, November 24th, 2012. Oh, there we go, November 24th, 2012. So we go and put in November 24th of 2012, and let's go ahead and just do 30-minute intervals. And we'll go into Mississippi, and Starkville, it's a town that kind of looks like its name. It's not the largest town. There is a state college in this town, though, but that doesn't matter. The sun and the earth are in fixed positions, and so what we see is here for Starkville, Mississippi, on November 24th, 2012, we have a map of the altitude and also the azimuth of the sun for every hour of the day. And so we go and we look to say, okay, well, what time of day is the sun casting at 160 degrees east of south so that its shadow is going off 180 degrees in the opposite direction. And so what we can see is this picture on November 24th was taken at 10:30 a.m. when the sun is 33 degrees up in the sky. And so now we know that the sun at the time this photo was taken is 33 degrees up in the sky. And so we can just use trigonometry, now that we know the angle of elevation of the sun and the length of the shadow, we can use trigonometry to calculate the height of that tree. And you might say, well, is that accurate enough? And the answer is it doesn't need to be accurate because trees grow over time. So whatever the height of the tree is, you're going to want to maybe look up that tree. If it's a pine tree or a maple tree, you might want to look at what the mature tree height is. This particular tree is a pine tree, but it's right next to some utility power lines. So I imagine if it got too much taller than it is to date, they might have to cut it down in the long run. But what we can see with PV Watts is it's a very valuable tool. We get based off the insolation data PV Watts provides. You can tell if it's going to be a sunny day or a cloudy day. For that matter, you can use PV Watts to see how many cloudy days in a row you go in your area typically before the sun comes back out, which is good for off-grid planning. We talked about yesterday, you can also get ambient temperature, wind speed, module surface temperature, the hours of operation for the array, what time the array starts or stops. Then you can go back to this sun angle azimuth chart and say, okay, well, at 9 a.m. on spring equinox, you go and plug in a different date and you get the angle of elevation of the sun. Correlate that with PV Watts to see, when the system is above, 20% power, and bada bing, bada boom, you can do your array layout sketch, roughly. And then for that matter, when you say, well, what about the ruler tool dimension for my rooftop? Is that going to be accurate enough? And it is pretty accurate. I mean, you can trust the dimensions. But anyway, you're still leaving at least 3 feet off the sides and 3 feet off the top of the roof for fireman access. And so if you're off by an inch or two, that's not the end of the world as far as remote assessment goes. So there's a lot of reasons to abide by proper fire code setoffs and not use every inch of the rooftop for your solar array. And one of them is that it lets you do your designs with remote assessments with a little bit of wiggle room in case you misclick on Google Earth. But say here's Half Moon's rooftop, and what we want to do is get kind of directly over that roof. Line us to north, and now we can click on one section of the roof and have to move the ruler tool, but we can see that Half Moon's building, that roof plane is 107 feet tall. And there may be some questions that you still have, like, well, does that overhang the building wall? And so do I, when I leave 3 feet off the sides, do I want to leave a little bit more because that maybe the edge of the roof isn't quite well supported? Do you have to go to site to get that information? You could just ask your client for a site photo. Everyone has smartphones now. So generally when I have questions, I just fire them off to the client and say, hey, can you take a picture of this? If you take a picture of that, even if this rooftop image is blurry, if the client just goes, 30 or 40 feet away and turns around, they can snap a photo of the rooftop. And so if you have a distant photo of the rooftop and you're looking at your Google Earth photo, sometimes you can say, okay, well, is this smudge actually a plumbing vent or is it just a smudge? And if you have a digital photo of the roof taken on site from afar, you can see where the penetrations are and correlate it with your remote assessment on Google Maps. You can also not just use Google, but their competition like Microsoft will also do that. Can you also use the Google guy to stand in the parking lot? Yeah, so sometimes you can use the little Google man to stand in the parking lot and get a view of it. Sometimes you can't. But what you also have is this 3D building view as well, which and you explore Google, there are ways now that they're getting into with their 3D modeling to actually measure the height of the building and the height of trees, and you can also kind of eyeball it too to say, okay, well, these trees are not tall enough to cast a shadow on the roof. So this 3D imaging is pretty good with Google Earth, and if you want to make some nice 3D videos of your project, you can get pretty good with the camera views. But the other part of this is, how is Google doing this? How are they taking a two-dimensional map and creating a three-dimensional object with such precision as to get tree heights and building heights and stuff like that? We'll show you some tricks of that. And then on top of that, there's also trigonometry, where if you know the height of the building and you can measure out the height of the dormer, especially with a street view, and you can see how sometimes the line here is actually calculating the three-dimensional distance. There's more features in Google Earth to help you fine-tune the rooftop dimensions, but generally I'm just clicking on one point of the roof and the other and measuring out the distances of the skylights and stuff like that. The next point, once you've sketched out the roof, solar design is literally, how many rectangles can you fit into your usable roof surface. So once you have that roof surface defined, you're just tiling as many panels as you can into it, making sure you're leaving enough distance between roof-mounted objects and that your array is somewhat accessible, especially if you're using things like microinverters. You want your solar array to be accessible at the edges in case you have to do any maintenance work down the road. But now that you have your roof sketch done and the modules across the roof, the next question is, well, how do you know how to wire up the modules to the inverter? And for that, we use software that's provided by the manufacturer called string sizing software. Now, in the intro to class, we learned that that temperature degrades module performance. And you can actually go into the module spec sheet and you get on the module spec sheet a number called you get temperature coefficients. And there's a couple. You get the temperature coefficient of voltage, the temperature coefficient of amperage, and also the temperature coefficient of power. And what we see here is that there's an inverse correlation between voltage and current. So as voltage climbs, current decreases. And as voltage drops, current climbs. But we also see that, voltage is a minus 0.4, whereas current is a plus 0.05. And so as temperature, and it's broken out per degree Celsius. So as temperature climbs, the voltage is dropping much faster than the current is increasing. And what that means is you get a reduction of power as temperature climbs. Conversely, under colder operating conditions, your voltage is going to increase and your current may actually decrease slightly. But again, the current is not really changing all that much, whereas the voltage is what's much more impacted by temperature. Now, the thing is, your circuits cannot exceed 600 volts. And so using the pencil and paper method, you would take the standard test condition voltage on the module sheet and then find your coldest design temperature and then adjust your voltage based on the coldest design temperature. And that would take these module voltages that are, maybe 33 volts at standard test condition, and it might raise it up to 40 volts under the coldest design temperature data. So you'd have to go pull up your ASHRAE database, find your cold temperature design data, and then make sure your system is designed not to exceed the amperage input and the voltage input of the solar array in a code compliant manner. Now, manufacturers want to make it as easy as possible for you to design a system using their product. So any inverter manufacturer, if you just Google the inverter manufacturer name, and the DC circuits are in the industry referred to as strings. And so if you just Google the inverter manufacturer name and string sizing, you'll get the software sizing tool that's provided by the manufacturer, which is free. The manufacturer wants you to be able to figure out what inverter goes with what module. Now, some of the battery companies are used to off-gridders who are maybe not even following code, but piecing together the design based off these temperature coefficients, etc. What we see here is we're going to pick out the IG Plus line, which is an older inverter product line from this inverter manufacturer, and we'll go and put in I've just recently installed a Suniva module. They're a US manufacturer, but they actually went bankrupt a little while back. Well, we can see we're choosing between 72 cell modules and other non-72 cell modules further down. So we're going to pick out a 285 watt 60 cell module, and this one might be the all black module as opposed to having a silver frame with a white backsheet. That B might be reference to all black. And so what we can see is that this particular solar module, now let me pull my spotlight back up, this particular 285 watt Suniva solar module with this particular Fronius IG Plus 6.0 inverter, what we have is a list of all the acceptable inputs that will be within the performance warranty of the inverter and the modules, so that you're not damaging. If I do 2 circuits of 9 modules each or 2 circuits of 13 modules each, either way, we're not damaging the inverter. We're not exceeding the 600 volt threshold. We're not exceeding the amperage input of the inverter, and the calculations are all done for you. Now, let's go and toggle some of these temperature conditions. Let's say I'm designing a solar array in Houston, Texas, where I know in the summertime it's going to get up to 120. So I pick 120, and what happened? Well, now that 2 strings of 9 modules is no longer available as an option. So you can see if I go to a hotter climate, what's going on here? Well, remember, as a hotter climate, voltage drops, so we're probably not exceeding any problems with voltage, but in a hotter climate, amperage will increase at hotter temperatures, and what's happening is maybe on this circuit, the 2 strings of 9, it's not really an amperage problem, because if it were, the whole circuit would drop out. What it is that on those hot summer days, the inverter is simply not getting enough power to turn on at 9 a.m. or 8 a.m. or 7 a.m. when it otherwise could be. And so we want to give those circuits a little bit more voltage so that in the early morning, voltage climbs enough to turn the array on. Now let's go and explore this record cold temperature. So, in Houston, Texas, even though it never gets below freezing, there might be the coldest design temperature might be back in 1930 when it got down to -8. And what we see is if I go from a 5 to 9 degree down to a -8 degree, we see the 2 circuits of 13 drop out. And so the 2 circuits of 9 dropped out simply from a performance issue. But the 2 circuits of 13 at this cold temperature, what's that saying is they've taken the temperature coefficient of voltage and they've adjusted it for your design temperature. And if you did that with 13 circuits, that would exceed the 600 volt limit at the coldest design temperature index. And so that's a code violation. And for those reasons, when you're doing your voltage checks, you're going to use the coldest temperature on record. Whereas the amperage check is not really a safety issue, it's more of a performance issue. So you don't need to use the record high, you only need to use the average high. But on the cold side, you need to use the record low for designing. Now that's unless you're using a module level corrector like a microinverter or a DC optimizer that will be doing the correction for you electronically up on the rooftop. So on a cold day, it might dial down the voltage of the system and increase the amperage. Now, this is for a Fronius 6.0 inverter. Why don't we go and look at one of their more modern inverters. So here's their Primo 6.0 inverter. And what we actually get now is two different power points. So actually, this Primo inverter, we could put 2 strings of 5, and then it says, okay, well, if you do 2 strings of 5 on one point, you can only do 1 string of 6 on the other. Otherwise, you're way out of range. But that's really saying the array may be oversized. If I did 2 strings of 7 and 2 strings of 7, and I put 8 kilowatts on this 6 kilowatt inverter, it says you might be oversized, but it's not telling you not to do it. It would flag that if it's not an option for you, if it's not going to work, it's not going to show up as an option here. So, if I'm doing an off-grid array, I might even oversize anymore. I might go to 2 circuits of 8 and 2 circuits of 8 and put 9 kilowatts on a 6 kilowatt inverter. And that's because when you're off grid on the sunny days, you're usually having all the power you need. It's those overcast days when your array is only producing 1/3 of what it otherwise would. That's when you need more power. And so depending on your application, if it's grid connected without batteries and you're selling all your power to the grid, we're oversizing our inverters by about 20%. In an off-grid setting, you might actually oversize the system by 40% or 50%, simply because you're going to have a surplus of electricity on sunny days anyway. It's really more about how can you produce more power on a overcast day. And so for that, it's, well, you either have to store it in a battery, which is expensive and short term, or you can just buy more solar, which nowadays, it's generally more cost effective to overload the inverter with solar capacity than it is to buy additional storage capacity. So anyway, we get our acceptable string configurations through this string sizing tool. The orange simply means that the array may be oversized. And so in the green range, it's like you're putting 4.5 kilowatts on a 6 kilowatt inverter. There's no oversized situation there. You're generally going to be designing in that orange range. It's a common practice to oversize the array capacity compared to the inverter output. And in fact, you can go into PV watts. Let's see, do I have my PV watts data from yesterday? Yeah, this is from yesterday. You can go into PV watts and you can say, okay, well, this is for a 1 kilowatt array, 1 kilowatt in Augusta, Georgia, and I have a printout for every hour of the day, every day of the year, and I can go to my, you get the temperature data, you get how much irradiance is actually going on the module itself, the temperature of the module, and then we finally get to AC system output. I can go and explore this data. I can see that the maximum value of this column is 847 watts out of 1,000 watts. And so, 847 out of 1,000, our system, the inverter capacity can be 84% of the solar array size before we lose any electricity at all. And then I could even go and say, count how many days this is above 800 watts. And as we said before in yesterday's class, often, if your peak is 847 watts, you're generally, for most production, 99% of the production of the array is not getting above 800 watts. And so, it's very common for the solar array to be 20% or 25% oversized compared to the inverter capacity. And there's a number of reasons to do that. Solar modules are cheap, relatively speaking. Solar modules degrade over time. So if you're a little bit oversized today, a few years into the array, you might not be losing any energy at all. It's just, is it bad to have an undersized array on an oversized inverter? Not really. You might even get longer inverter life out of it. It's just to efficiently use your equipment, you're in that kind of 20% range. So back to our program, where, after you can tile how many modules, you use, so what you do is you pull up Google Earth, you measure out your roof dimensions, you analyze the shade, you get your building height off the shadow, you get your tree height off the shadow, you compare the two, you pull open PV watts, you get that hourly data, you find where your solar window is, you look at where those shadows are under a variety of extremes in combination with your sun angle azimuth chart. And then you go and you do your string sizing, you select your allowable circuit configuration. It may be that you have, in this design example, it may be that you have, you can fit 30 modules on the rooftop. And so I would be doing, 2 strings of 7, that would be 14, and then 2 strings of 8, that would be 16. And so I can fit my 30 modules. But if I had 29 modules on the rooftop, that would be much more difficult to hone in on. And it might be that based off my string sizing, if I'm doing a nice aesthetic rectangular array, it may be that based off my circuits and based off my array, that I have to remove a module from the system to get the circuits to work. And in that case, I'll often recommend putting a solar module up on the rooftop just to hang out and not do anything, just to make the array more aesthetic. And that way there's a module that's up there that if one module does happen to go wrong, the problem is when you replace the modules down the road, it becomes hard to find a form factor that's your exact match because technology marches onward. Now, you can usually buy old modules out of inventory, but once you get 5, 6, 7 years into system ownership, that inventory is commonly depleted too. So, having an extra module is not the end of the world in terms of, cost effectiveness. Your racking companies also have sizing tools. And so when we look at how many attachment points, how many clips we have, what's the right size of the bolts so that the clip matches up with your module frame in an aesthetically pleasing fashion, you might say, well, do I have to do my array layout and then determine how many feet of rail I need and then look at their availability and say, okay, I need 8 sticks of rail, and so I need 6 splices for the rail, and then I have end clips for attaching the solar module to the rail on the end, and then I have mid clips that attach to the solar modules in the middle. How do I specify my racking balance of system material? Well, just like an inverter manufacturer wants to make it easy as possible for you to design a system using their product, racking manufacturers want to make it as easy as possible for you to design a system using their product. So here I have the array layout complete, and I have 2 rows of 3 modules, 2 rows of 3 modules, 2 rows of 4 modules, 2 rows of 17 modules. I'm putting that into the manufacturer design software, or you're building a map. So this is a different manufacturing design software, and you're simply putting in the array layout. As you can see here, where we've built our array layout, and now we're removing the spaces required for the skylights and that little mini dormer. And then just like with the string sizing software, we're putting in our site conditions. For racking, it's a little bit different. You know, they need to know your 30-second wind gust speed. They need to know your snow load. So this is stuff you can find in the ASHRAE database or online. The exposure category is also important. You know, or if you're inside the city, you have natural wind barriers blocking that wind. But if you're on an exposed plain, you know, it's not quite the same. Since we're on the topic, here is a picture of a solar array that's in an exposed setting on this hill. And so what you can see is around this utility scale solar array in the Virgin Islands, you know, there's not much underbrush on this bottom side of the hill here. And so when Irma came through, you know, while Florida wasn't really impacted, some of the Virgin Islands got a big hit, and we can see that not all the solar panels stuck to the racking. You know, maybe they needed a little bit more robust module clips to stay in place. You know, this kind of destruction, you know, the hurricanes are one of the most, you know, especially Category 4, Category 5. It's the wind speed of a large tornado, and you know, you can't solve everything with that, but we can see that, you know, in this exposed area, you get a little bit more force. So in this racking software, they're saying, okay, well, tell me about the structural beams and how you're attaching to those structural beams and what the spacing is between your attachments. And it has you, you know, put in your roof map and site details. And then at the end of it, it says, okay, well, we have 3 different racking products, you know, XR10, XR100, and XR1000. And the difference between these is the rail thickness. Let me see my mouse here. Your rail thickness, you know, you have your solar rail, and there's actually a little top channel in this rail for the clips to go into, and a little side channel for the roof attachments to go into. And so your clip is a bolt that slides into here, and then it has some wings on it. And these wings just kind of clamp down on your module clips, your module edges, and then your rail, you know, you're running across your rail, and your modules get kind of just pressed down onto the rail. And then you have a attachment point called an L foot, and the bolt goes into this channel, and then your lag screw goes through the L foot into the rafter. And more of your top quality L foots nowadays might have 2 lag screws to prevent this L foot from trying to torque up, which is common in heavy snow loads, where you get a lot of weight going down. You might have the L foot actually trying to torque the other direction. Well, what I really wanted to point out here is that the XR10 is a thin rail gauge, the XR100 is a medium rail gauge, and the XR1000 is a super strong, thick rail gauge. And then we can see in Zone 1, Zone 2, and Zone 3, and what are these zones? These are the roofing plane wind zones, where Zone 3 is the corners of the building, Zone 2 is around the edges of the building, and Zone 1 is the interior of that roof plane. And what we can see is as we get towards the corners of the rooftop, the wind speeds pick up, and we can see that, you know, the strength of the racking is a little bit weaker than in those reduced wind settings. We also have a few other things on here. We got the max cantilever. And so what that means is here's your L foot. That's the side view. Let me draw it on this other part. So here's your L foot, and here's the slot that goes into the rail, and your rail's coming along here, and there's a little channel that the rail goes into. And this slotted L foot allows you to kind of level the racking up and down so that if your roof surface is not completely level, you can do a little bit of squaring of the racking to accommodate a slightly uneven roof surface. But the max cantilever refers to at the very end. Here's your edge of your solar panel, and then at the very end, there's a bolt that goes down into the end, and the clip only has one kind of flange on it, whereas in the middle, it would have two flanges. And so what will happen is you'll put your last clip on, and then you'll take a sawzall or a reciprocating saw and saw off the remainder of the rail, and then put a little cap over the remainder of the rail. And that way, your attachments and all your wires and cabling are hidden underneath the solar array. And the solar array kind of achieves this levitating effect where the solar array is just kind of, it looks like it's just hovering slightly over the rooftop. And that's simply because, here's your module edge, and here's this little clip you don't really see, and then your attachment points are underneath. So you can, with an internal wire run where your wires are going into the attic from underneath the rooftop, you can actually contain all of your cables and all of your attachment points underneath the array, which preserves array aesthetics. And I think that is going to be essential in preserving your property value as you go along. Now, when I did the design for Half Moon, I called up the sales rep, and he said, "Oh man, you're going to love our new racking system. It's the XR1000, and we can actually do up to 10 feet between roofing attachments. And so that means you have fewer attachment points, and that means your solar array is less likely to leak." Well, I mean, that's what most people think. I have a different opinion on that. Here's your L foot. That's your roof attachment. And usually nowadays there's some flashing that is integrated into the L foot. And then you have your lag screws that go into the deck. And this is a brand new penetration. And your every shingle on the rooftop has roofing nails going through the roof, and they don't leak. And your brand new solar attachments usually don't leak. What leaks are pre-existing attachments that have been on the rooftop for a decade, like a plumbing vent or a skylight. And as the solar installers are up on the roof walking around those pre-existing penetrations, they're weakening the attachment point, and maybe the sealant that goes and seals the whole around the flashing, maybe that sealant has dried out, become brittle, and all the tromping around on the rooftop busts it up and water can get into it. So it's usually not the brand new solar attachment that leaks, it's the pre-existing holes on the rooftop that are not part of the solar array that get weakened during the install, and generally they're the ones that start to leak. Furthermore, when you have this attachment point, you have to think, well, what causes a leak? Is it the fact that you actually poked a hole in the roof, or is it the uplift and downlift and tangential forces on that lag bolt that goes into the attic? So over 10 years, 20 years, the wind is picking the array up and slamming it back down and vibrating it back and forth. And so is it the attachment that causes the leak? And if so, there's not much you can do about that other than not do the project. Or is it the force on the attachment that causes it to leak? And how do you reduce that force? Well, you put more attachments rather than less attachments. And so now your forces are cut in half rather than applying all of that force across one attachment. And so kind of counterintuitively, if you use more attachment points rather than less attachment points, your array attachments get less force on them, and time will tell, but that should help you not leak so much. And so on top of that, your rooftop may not be able to handle the forces of those long spans. If you go into a 2x4 with a lag screw, you have plenty of holding strength, but then it becomes, well, how does the roof truss transfer that load into your support walls? And so you could, you could potentially overload the truss at one particular point. And so what's very common as a structural engineer, I'm not a structural engineer, but I tend to run all of my projects through structural engineering, and like on metal rooftops in particular. Metal roofs are generally built just to within spec, whereas your standard pine rafter surface board shingle is kind of over engineered. And so I've often come to or my structural engineers come to the conclusion on metal rooftops. And I told the sales rep here who's trying to sell me this XR1000, I say, now wait a minute. My structural engineer is not telling me I can do 8 foot on center or 10 foot on center. In fact, my structural engineer is not telling me to go 7 foot on center or 6 foot on center. But for this particular metal rooftop, which is a less expensive, weaker metal roof, my structural engineer is actually telling me I need to go 2 foot on center rather than anything greater than that. And the sales rep goes, well, what are you talking about? I've never heard of a 2 foot on center attachment point. And that's because when a racking company talks about the engineering of their racking, they're talking about whether or not their racking will hold together during a hurricane or whatever. But they don't know anything about what you're attaching it to. And that is, I expect a racking system to stick together. So I don't, if I'm buying a racking system that's rated for 120 mile an hour wind, I should hope that it will be able to withstand 120 mile an hour wind. But, what I'm talking about is the structure. And so it might be that if you're going into a 4 foot on center span, which is standard practice, 4 foot on center staggered, or if you're being even more aggressive and going with a 2 foot on center span, you may not need the most robust rail in the world. It might be that you spend more money on attachment points and less money on rail, but you're still going to stay within that cantilever and achieve that hovering effect. It's just, the rail is there to support the frame so that not all of the force goes into the frame. But having a thick, robust stick of rail up on the rooftop to reduce attachment points may end up causing more trouble rather than saving you trouble. So again, the racking companies are going to tell you what works for their systems, but then it's up to you to apply your engineering know-how for that. And what we can see again is this is really why I like using Iron Ridge as a racking company. Most solar racks are the same. And most solar panels, for that matter, are the same. So it doesn't really matter if you go with manufacturer A or manufacturer B. But I found that at the residential level, engineering data is hard to come by. At the commercial level, when you're doing a $300,000 up project, the racking company, if you have engineering questions, they have engineers on staff. And between your building structural engineer and their team, on a larger commercial project, they'll work with you to do load analysis on where any attachment points would go. At the residential level, that data is not available. And so I found that Iron Ridge is one of the only companies out there who will actually give you a zone 1, zone 2, and zone 3, uplift and downward and lateral force on each attachment point. And what we can see is that the uplift force in zone 1 is about a third of that at the corner of the array in zone 3. So we're going to come back to that a little bit later. You also get the total weight of the array and then the weight per attachment and the distributed weight. And, I have found, especially on flat roofs, it might be that the flat roof is rated to take the additional distributed weight, but the decking may not be rated to take that weight. You may have to apply the load directly on top of the support beams. So we're going to come back to that in a minute. So looking at your racking components, this would be an end clip that goes at the edge of the array. This would be a mid clip that goes between two modules. And here we see our 4-foot on center attachment points that are staggered throughout the interior of the array, that are well within spec, and also evenly distributing that load along the rafters that are underneath the array. Now, down here at this corner, you can see that they've deviated from the 2-foot on center, and now at the corner of the array, you have 2 attachment points that are 2-foot on center instead of 4-foot. And actually, one comment I have about this particular racking is at this corner, they didn't put in that extra attachment. And I think, especially if you're going all the way to the edge of the rooftop, you absolutely want to reinforce the corners of the array, because we can see from our engineering data that at the corners, you got a lot more force than inside the array. Now, a lot of installers aren't doing that because they completely ignore the structural engineering aspects of the project, which might, our audience members consist of engineers. That concept might make you cry a little on the inside, because it suggests that there could be some bad practices going on in the industry. And this is exactly one of those bad practices that results from residential permit offices not requiring structural engineering oversight on solar arrays. And for that matter, on a pine rooftop, you're generally going to be okay. On a pine rooftop where you're going into the rafter, the pull strength is hundreds of pounds per attachment point. So, as long as they're hitting the rafter, this array should be fine. But if this were not a pine roof, but it were a metal rooftop, if this were in a hurricane zone, not a 90-mile-an-hour wind zone, that might not be the case. And so, the danger is if you're skipping over the structural engineering process, you might come across a rooftop that actually needs more robust support. And if you don't provide it, then you can make a design error. And furthermore, installers say, well, I don't like doing all these attachments because that's more money and more time spent on the rooftop. But then there's other issues to consider. Firemen are very concerned, not really about what the solar industry thinks they're concerned about. The solar industry is like, oh, rapid shutdown and rooftop access. Okay, so and John, I do update my presentations from time to time. If you want access to the updates and the revision list, just join my Slack community, because that's where I do like audience follow up and stuff like that. There should be a link in the chat box for that, or you can just get the link by visiting my website. But then going into the So anyway, it's worthwhile to do your racking engineering. And on the fire safety concern, basically by using this additional rail and going into each rafter, you're providing some additional support strength along that roof surface. And so, firemen right now, they're scared of solar because they want to, this does not have the 3 foot up off the top and 3 foot off the sides for a fireman to get up on the rooftop and cut a hole. And that's not uniformly enforced across all jurisdictions. And there's ways to get out of it. To ventilate the building, you could have a forced air ventilation system instead of passive. And so that if you have a roof cap, if you have a vented roof, the ventilation may not matter so much. The fire code access may not matter so much. But what firemen are really concerned about is the additional weight on the rooftop, causing the building to collapse earlier than it otherwise would. And that's not just a solar problem. That's, a tile rooftop problem and, all these sorts of things. The point is, hey, there's actually some structural advantages to be gained from solar, and you can design a solar array in a fire code compliant way such that firemen should actually love the fact that solar's on a rooftop, because it should mean that they get a little bit more time in the building before it collapses. But because the industry doesn't know that, that message is not being pushed out there. But if you ever see a building with like, in the Japanese tsunami, I saw a building floating down the street with a solar array on top, and the solar array is happily floating along. Here's a rooftop where, I've seen a rooftop where the building burns down and it's not the solar array's fault. And the only part of the building that's still standing up is the section of the building frame that had the solar array on top. And then I also saw a Hurricane Irma picture where the rooftop from the north side was sheared off, and then this part of the roof was gone, but the bottom part of the roof with the solar array on it was still intact. Solar does provide some structural advantages. And so again, the best practice is to stagger your L feet 4 foot on center, and then add, reinforcements around the corners of the array, just to make sure you're over-engineered and in the clear. So we put in how many rows of modules we have into our racking design software, and it comes back to us with, okay, for this section of 3 modules, 3 columns and 2 rows, you're going to use 10-foot rail with 2 sets of it and 12 attachment points and 8 mid clamps and 8 end clamps. And then for this longer section, we have a lot more mid clamps and the same number of end clamps. And instead of using 2 sets of 11-foot rail, they're saying, okay, we make rail in 14-foot sections and 11-foot sections. And so for this section, you're going to use 1 stick of 14 and 4 sticks of 11. And this is about as much construction data as you're going to get out of manufacturing, of manufacturer provided documents. So if you're really interested in enabling your mainstream contractors to do solar, you're at this point, it's up to you to take this data and then generate a construction scope document off of it. Otherwise, you're just going to be using generic install manuals that tell the contractor how to put together the racking system, but it's not necessarily going to be customized to your job site. And so finally, we get our complete balance of system material list. And so here on our input screen, I guess it's not telling us. Maybe we'll see another input screen where it suggests it. But when you're doing your racking design, you're putting in things like the spacing between your roofing attachments, which are these lag bolted L feet. And then also, if you're using microinverters or module level panel electronics, you need the hardware to mount those as well. And it'll give you ask you, are you using power optimizers, 1 per module or 1 for every 2 modules? And it'll put that additional balance of system material for the attachments into here. Now, another note to point out, on this rail, there's this top channel that runs along the rail. And if you notice in this T-bolt, the question is, here's a hex head bolt and here's a T-bolt. Now, do you have to use a T-bolt? Can you just go to Home Depot and buy regular bolts for the array? And the answer is, yeah, you can. But at that point, there's a channel at the end of the array. And if you use this hex head bolt, you got to slide all of those bolts down that channel. And then, these stainless steel bolts, they're not designed for multiple use. And so if you take them apart when you're installing, and you get the first 3 or 4 modules on, and you realize that you didn't square the racking, and so the modules are trying to creep up at an angle because your rails are oblong and you're trying to bolt a rigid rectangle to an oblong surface underneath, and it causes the modules to torque and skew. And so then you go and you remove the bolt and clip and try and reset it. Well, what strips is that threading on top of the bolt. And so if you're trying to service a module that's in the interior of the array, you can just take the clips off and pull that module up and get to the microinverter that's underneath it. But the danger is you may strip the bolt in the process. And what this T-bolt allows you to do is put that T-bolt into the channel and then just give it a quarter twist, and it'll just lock into the channel. If you have a hex head bolt, you'll have to remove all of the modules until you get to the end and then rethread that hex bolt all the way down to the module you're servicing. And so if there's one piece of equipment when you're doing your racking that you really need to over order, it's actually these T-bolts right here. That's a specialty component made by the racking manufacturers that you just can't find locally. You have to buy these T-bolts online, and it's absolutely, you don't need extra clips. That clip isn't going to be damaged during the install. That mid clip isn't going to be damaged. If you drop it or lose it, there's no harm in having a couple extra in your toolbox. But as far as consumables, it's this T-bolt that is definitely worthwhile to order a few extra of. And so that the reason why I mentioned that is then when you finally get to your balance of system material list, the T-bolts are being included in your end clamps and your mid clamps, and you may need to tell your distributor at that point, hey, can I also buy a few extra T-bolts? And if you can't, then you can find them online, but they're good to have on site. All right, so now we have our interconnection. And what we have to decide is, how are we going to interconnect to the array? Are we going to interconnect between the meter and the main service panel, or are we going to wire the array up to a breaker on our service panel? You can actually do either or, but then we get into a National Electric Code rule called the 120% rule, and it's gone through a couple of iterations in code. So it used to be called the 120% rule because what it said is, if this is a 200 amp service panel, you can put an additional 20% of breaker capacity there. So you could put 20 amps of breaker sizing and on a 100 amp panel, or you could put 40 amps of power onto a 200 amp panel. And the reason why this is a concern is this panel is commonly rated for 200 amps. And so if you feed in 200 amps from the utility and you feed in 40 amps from the solar array, and you have 300 amps worth of breakers, theoretically, you could turn on all the appliances in your home and draw 200 amps from the grid and 40 amps from the solar array, and now you have 240 amps of current flowing through a 200 amp panel. And when that happens, the panel could heat up and start a fire. And so the reason why you're allowed to do this oversizing is because you're connecting to the very bottom of the bus bar and you're not oversizing it substantially. And so what they're saying is the power from the grid will flow out to those currents, and the power from the solar array will flow out to the other loads, and you're never going to have this current meet up in the middle. And so the bus bar itself is still in that cross-sectional area, not exceeding 200 amps of flow. You lose that 20% if you just tie in anywhere on the service panel. So you have to tie in on the load side onto the bottom of a service panel if that panel has both loads and lines. Now in commercial design, you're generally having a dedicated panel, and this might be like a 200 amp panel, and you might be tying in 200 amps of solar into it. So if the total breakers of this panel do not exceed 200 amps, then you can just tie in the solar wherever you want. But usually on a residential panel, your service panel is overloaded and these additional National Electric Code provisions apply. Now, what I think is much simpler and more forward looking is to tie in the solar array between the meter and the main. And there are cases, especially with smaller solar arrays, where you don't need to do that. But there's also cases where you have a small solar array and it's just much better to do this line side connection. Now, line side connections are only allowed under particular circumstances, and those are for energy management devices that are on site. And so a line side connection, you might get a jurisdiction telling you, oh, well, most of the solar installers in our area just do load side connections, and we don't want you intercepting the power lines between the meter and the main. We want everything on the customer side of the breaker. And at that point, usually I have to call the utility and say, well, look, we want to do a line side connection and you're telling us we can't. And they'll say, yes, that's right. And I say, well, what if we want to add a whole house backup generator to the property? And we want to put in a transfer switch that doesn't protect a critical load panel. I mean, if you tie into the load side, you could put a critical load panel off of that with a battery and power it during a blackout. I don't like critical load panels. I like powering the whole entire house and letting the client manage their energy. But, you know, if you're trying to power grandma's insulin refrigerator, then a critical load panel makes all the sense in the world. That's the last place you want to run out of electricity. But if that electricity is not serving any kind of emergency backup purpose, I would rather power the whole house and then let the client decide how they use that electricity. And furthermore, many solar arrays that are trying to offset 100% of the on-site power usage, there are energy efficient homes where a load side connection is all you need. But if you're looking at it with the load side connection, you can connect about 40 amps, and that's going to be a 240 volt service. And what that means is the maximum output capacity of the system is going to be around about 9.6 kW or so. And often on a large residential home with a giant roof in the southern part of the United States, which are systems that I work on a routine basis, a 10 kilowatt array or a 12 kilowatt array may be just enough. You know, the average home in the United States uses 11 megawatt hours of electricity. But in the South, the average home, because of our higher electric loads, uses 14,000 kilowatt hours. And so we know our golden ratio from yesterday with PV watts. You know, if I'm producing 1.4 kilowatt hours for every watt in my system, you know, to get 14,000 kilowatt hours, all I need is about a 9 kilowatt system or a 10 kilowatt system, and I can make that. So I could, for most homes, do a load side connection and knock out 100% of my bill. But your solar customer, you know, there's solar customers who are very energy efficient and they might only need a 6 kilowatt array. There's also solar customers who are energy hogs, and that's why they want to reduce their electric bill. And so you might need more than that 20%, at which point a line side connection makes all the sense in the world. But on top of that, you know, let's say I need a 10 kilowatt solar array. And so I do a load side connection with my 10 kilowatt solar array. And then down the road, I want to add a battery. Well, I've taken all of my capacity on a load side connection with my solar array. And so when I go and add a battery down the road, I'm still going to have to do a line side connection. And so I would rather just start with everything being a line side connection. And that way, when you add batteries down the road, maybe the best solution, and there aren't inverters out there who are supporting this right now, but maybe the best solution down the road is to have two batteries, have a lead acid battery bank for your base load and a lithium ion battery for your variable loads. Who knows what you're going to need for the home of the future. But what I do know today is through a line side connection, I can go all the way up to my service panel rating. And so I might do 60 amps of solar today and then 40 amps of batteries tomorrow, and I'm still, only 50% full up. Maybe I want to add a generator on top of that, and that might be another 40 or 60 amps. Maybe 80 amps. Line side connection is the way to go to start building a comprehensive on-site, what manufacturers would call a service panel that you put right here on your line side connection. This is not your main service panel. What you would call that would be a power distribution panel or an energy distribution panel that is not considered the main panel, but that's between your meter and your main breaker. It's all on the customer side of the meter. So, from a dollar and cents perspective, whether or not you're doing a line side or a load side connection is all the same. Well, we've determined, we fit all the rectangles onto our rooftop, and we know how many circuits we're going to have from our string sizing software. Okay, so we do have a question. What if you already have a full backup gen set with a transfer switch? Where to connect? So, let's say this is your home and you already have a transfer switch, and this generator is let's say it's a 50 kilowatt generator, and it's fully taking up all the capacity of our line side connection. You could still do a load side connection. It's you have both sides of the service panel to work with. So it's not, load side connections, if you've already done a load side connection or whatever, or it's just more convenient it's not the end of the day to do a load side connection. Sometimes it's going to be better if you don't want to have batteries to tie in your solar array on the line side and then have a generator do a critical load panel, or tie in. You could also tie in here. This will better answer. Let's say you have a automatic transfer switch right here. You could still go and tie in the solar array between the transfer switch and the meter. And the reason why you would do that is during a power outage, that would kill the solar array. And you might say, well, hold on. During a power outage, aren't we trying to turn the solar array on? And the answer is, yeah, you can do that, but you need an energy management system on site to do that. So you don't just need a generator and a battery, but you need a battery inverter that can act as the controller. Because if your generator and your solar array are not separately derived, they're going to try and fight each other unless there's a control system saying, okay, well, we have the storage capacity for any surplus power to go into through our depleted battery bank. And so let's turn the generator on until the batteries get up to 80% capacity, and then we'll turn the generator back off. That's one way to do it, but that's an expensive way to do it. Until batteries drop, you could do a line side connection to your, and then just have the generator run the house during the power outage. And then later, let's see, I'm losing power here. Hold on one second. No, I'm plugged in. What's going on? I don't know. Oh, it's my screen is fiddly. Okay, so Let me make sure my hardware settings are all, yeah, they're all good. Okay, so you can tie it into the line side and not have that backup power if you want to. And then and the reason for that is now that your transfer switch and your generator are all in the same place down the line, it's easier to retrofit a battery bank in addition to the generator if they're all in the same spot in terms of interconnection. But you could have the solar array here and maybe put a motorized breaker so that and develop your own control system. You know, when you get into batteries and on-site generators, there's a lot of on-site specific customizations for your specific purpose. All right, so in your array layout, you know how many rectangles are going to fit on the roof, and you know how many circuits are going to be wired into the rectangle. But what you don't know is physically which modules on the rooftop are going with which circuit. And there's a few different ways to do this. Remember with a string inverter, you have 12 modules per circuit and 2 circuits or 3 circuits. And then all the circuits have to have the same number of modules on them for each PowerPoint tracking device, which the inverter nowadays may have 2 or 3 PowerPoint trackers. That didn't used to be the case. So it used to be that with string inverters, every circuit on the roof had to face the same direction and had to have the same number of modules per circuit. With microinverters, you could have 17 modules on one circuit and 12 on another, and all the modules could be facing any direction. Because with microinverter systems, every module on the roof is effectively its own solar array that's tied into the grid along that branch circuit. With DC optimizers, it's the same way. You can have strings of different lengths, panels facing different directions. But even so, you'll have branch circuits for microinverters, strings for DC optimizers, strings for string inverters. And you might know how many modules are going on the circuit, but you don't know which modules are going on which circuit. And so here we have a numbering system where I have circuit 3, and it's 17 modules per microinverter circuit, and circuit 4, and it's 17 modules per microinverter circuit. And just that, a happy coincidence is that's how it lays out. And so I have my circuit connectors on the end. And then on the south side of the rooftop, I have 3 different subarrays, and I have 2 circuits between 3 subarrays. And so I have a couple of options. I could do this on circuit 1 and then go into the roof and then come out here and put these on their own circuit. So I have a 10 module circuit and a 6 module circuit. But just in terms of voltage drop and balancing, I could also instead go into the roof here and come out this way. And that way, instead of having 10 on one and 6 on the other, I have 6 on one and 8 on, or 10 on one and 6 on the other. Instead, I have 12 on one and 8 on the other, and they're just a little bit closer together. So what I might actually have is underneath this rooftop, I might have my if the point of interconnection is right here on the side of the building, I might have this circuit come here and then go into the roof. And then below the roof, I might have a box where I take this circuit and wire them together. And then for this circuit, I'll go into the roof here and then go into the box as well. And then I'll take those 2 circuits from the box to my service panel. And that's to kind of reduce wire sizing. And now on this array, it's pretty straightforward. But the problem is if you start adding, a lot of rows and a lot of panels, let me try and make this a little bit more clear for a minute, because this graphic does not really illustrate the point very well. So let me just draw it for you Need to go update my slides a little bit. But let's say I have a block of solar panels on the rooftop. So here are my panels. I'll just draw them out just really quickly and make it a little ugly. But here are my solar panels on the rooftop. And I have to determine which panels are going on which circuits. And so when I was brought into the industry, what I was told, and let me, fill solid color. Yeah, so let me just square this off real quick, and that'll make the illustration a lot easier to understand. If I'm looking at this solar array, I would go, okay, the modules, if there's let's just go and say 11 modules on a circuit coming from our string sizing. I would go, okay, I'm going to go 1, 2, 3. Let me make this a little thicker. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that would be on circuit A. And then circuit B, I'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that would be circuit B. And then on the next circuit, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that would be circuit C. And then these three modules, I might go back and say, okay, well, actually, I have 3 more modules and I have 3 circuits. So if I'm allowed to do 3 circuits of 12, I make that circuit 12, and then I have this circuit, and that's 1, 2 extra. And then now with 12 modules per circuit, it's all nice and neat and organized. And I would call this the snakes in a basket approach, where your circuits just kind of snake through the array, where one stops, the next one begins. And, you can see how that's, I call this snakes in a basket, because the circuits just kind of, stop and start right next to each other. Well, the problem is, especially with microinverter arrays, but even at a larger level, a very common failure point in the system are these custom-built connectors that go at the start and stop of every system. And so what we can see is that some of our connectors are located on the edge of the array, where they're accessible if there's a failure point. But as you can see, the problem is these connectors here in the middle, if they fail, you're going to have to start taking the array apart in order to get access to those connectors. And so lately, when I've been doing my solar design, I might take a step back and say, well, do I have to do 3 circuits of 12, or can I do 4 circuits of 9? Because if I can do 4 circuits of 9, I can have my, circuit, 1, and then my circuit 2, and my circuit 3, and my circuit 4, and have my connectors all accessible at the edges of the array. And then for that matter, I'm looking into multiple power point tracking string inverters so that I don't need to have any module level electronics inside the array. And that way I know, usually the manufacturer provided connectors are the same. And so they just click into module A, module B, and they're all built by machines or handmade by someone who knows what they're doing at the point of manufacturer. But these field built connectors are commonly problematic. And that's because even though it's a standard connector, it's not the best design standard to begin with. And then you have 4 different companies making the same clip, and they're all slightly different from each other and slightly different than what the manufacturers provided. So that clip tolerance is, like Apple makes really tight tolerances on their products so that when you plug in your iPhone charger, it stays in, whereas Droid, you go and plug in the charger, and after about 6 months, it starts to becoming really loose, and you have to either get a new phone or a new cord or something. The MC4 connectors are more like Droid than Apple, where depending on which ones you pick, the connections might not be completely tight, and if they're not made tight, they'll start arc faulting and triggering an error in the inverter and shutting down, and especially during commissioning process. And so, it's just better to try and locate your circuits along the edges of the array if you can. And that might also mean that it's not always a perfect scenario, but that also might mean that you do like circuit one. If you're doing 12 modules a circuit, you might go, one circuit might be 1, 2, 3, 4, 5, or even better, you might go like that to put, all of your circuits to be accessible along the edge of the array. So that's kind of a finer note, is that, when I got into the industry, it was all about cost reduction. So you'd want to use the fewest number of circuits possible, because that meant less material and slightly, some more balance of system material savings. Nowadays with cheaper modules, you can do larger systems, but with these module level electronics, the maintenance issues become into play. Now you don't have that Solar Pro making every single connector, but a lot of new installers doing this stuff for the first time. Maybe you have non-electricians making those connectors, and it's just better to locate them at the edge. Let's get back into our solar array. And of course, your manufacturers, if you have questions about the wiring systems, they have more than just string sizing software available. They'll have installation manuals, sample wiring diagrams, and if your electrician is good enough, they're going to be able to look at a wiring diagram, and even if they've never installed solar before, they can look at something like this and say, well, what it looks like is that I have a double pole breaker tying on to both legs, leg one and leg two of power, and I'm pulling those up to a junction box that might be installed on the rooftop or might be installed underneath the roof in the attic. And then I have leg one, leg two of power, and I see I'm also pulling up a neutral and also pulling up a ground. DC systems don't have neutrals, but you're probably still going to pull a neutral up to this junction box because that neutral circuit is also used as a communication circuit. And so if you're trying to trigger a rapid shutdown combiner box on a DC system, you still need that neutral wire there for communication. And then your system ground, of course. And so here, the electrician may not know what they're doing, but if you talk in their terms, like saying, well, what I need you to do is run me a 240 volt branch circuit up to the rooftop and terminate in that roof mounted combiner box, they can get right to work. So it's all about, they've never done solar before, but all this stuff is pretty plug and play. Now let's watch, let's take a break for a minute and watch a video. This is of a microinverter system. Actually, this particular system has been replaced by newer tech. But here's a microinverter, and these are the plugs that the solar module plugs into, called MC4 connectors. And what you can see is they after installing the railing, the microinverters just get bolted to the edge of this rail. And then here's a specialty trunk cable that comes from the microinverter manufacturer. And that gets bolted to the rail. And then you just plug and play the microinverters into there. So this is not stuff that any electrician should be afraid of. And then here we're just going into a roof mounted junction box, running our tray cable into the junction box, and then maybe landing on a terminal block with our wires. And as we talk about in our National Electric Code class, the main thing on how do I know what wires to select, it all comes down to their temperature rating and their environmental rating. So the wires inside your home are rated for dry conditions. The wires that you need to run up to the rooftop, they need to be rated for wet conditions, and exposed wires need to be rated for sunlight resistance. And now they're setting up the monitoring system. And so, it's any electrician, they encounter products that they've never installed before on a routine basis. If you can provide them with wiring diagrams and installation documents, they might take a look at it and say, actually, I can do this. So we wanted to use Half Moon's electrical contractor for the install because because they, we wanted the same electrician responsible for the rest of their building to do, this wiring work. But the problem was their electrical contractor had never done solar before. And so you call up your electrical contractor and you say, you want to do a solar install? They'll say, we'll let the solar guys do it. But if you call up the electrical contractor and say, hey, we're doing solar, but all we're really doing is running 5 branch circuits up to the rooftop and landing on a terminal block, and everything else is plug and play, then they'll say, I've never done solar before, but that seems easy enough. And now all of a sudden you're getting into cheaper labor that is not necessarily worse labor. It may actually be better labor because, you can't tell me an electrician doesn't know how to bend conduit and pull wire. They just need a little bit better direction from the designer, and there aren't many designers in the industry right now. This was a material list that I made recently for an expansion project where the system owner had done 8 kilowatts a couple years ago, and then he wanted to self-install a 4 kilowatt branch circuit. And just using these techniques, in a matter of minutes, we're able to generate a racking bill of material. We know how many microinverters we're using, and we know our solar modules, and pretty much everything else from that point on, particularly with microinverter systems, we're just dealing with AC stuff from that point that we could find at Lowe's or Home Depot. And so it only took, a matter of about an hour to come up with this specific specialty material list. Then it comes down to purchasing it. And the vendor that, we had to do a little bit of research because we were, the hardest part of designing a system expansion is finding an obsolete solar module that a vendor still has in inventory. And so we had to find a module that it's not the same module as what he had up on the rooftop. And sometimes the color of the silicon itself can be a little bit different too. But generally, modules of the same size use the same original equipment manufacturers, and it's not that big of a deal. If you're using all black modules from the beginning, then those will visually blend well with other all black modules, even if they're not necessarily the same size. But anyway, we tracked down a module of the same size as his original system. But the problem was the manufacturer who had that was a manufacturer, and they're rare in the industry, but this one was one of the largest online distributors. And the largest online distributors will only deal with, solar installers who are registering for their contractor program. They don't want to sell to a one-off project from a do-it-yourselfer, and that's who the client was in this case. And so I was able to call them up, the distributor up, and go through the automated calling features, and they say, well, if this is a do-it-yourself project, please call our partner for help on residential do-it-yourself. And that's really what we were doing. But I knew that if we called that residential partner, we wouldn't get the same pricing from the distributor as what we would get from buying the material through that third party middleman. And so at that point, I just ignored that and got through to a sales rep. And when you talk with the sales rep, instead of saying, oh, we're doing a do it yourself residential project, it's, oh, I need these part numbers and I see that you carry them, and I need this part number and I see that you carry that, and these old Jinko modules that you still have in inventory, I'll help you clear out that inventory. And we were able to buy these modules for 50 cents a watt, and we were able to buy the microinverters and racking components from them too. And so all in all, this 4 kilowatt install only cost the client $1.67 per watt. And in Mississippi, where we don't have net metering and we have very and not many solar programs to speak of, getting that lower price point was necessary in order to just get the project out of the ground. And so there are some advantages of doing an array layout sketch and developing this balance of system material just so that you can get more sales reps involved in quoting your system and getting your material price down. Okay, so let's go into computer-assisted design capabilities. 3D modeling is very helpful. This is Aurora Solar. We saw a little bit of them yesterday. But what you can see is instead of going out to site, you're actually building a 3D model of the site. And they incorporate LiDAR data, which is topographical information, where you can actually get the volume of the trees and the slope of the roof and even the height of the chimney. So that's pretty cool. What you see in this picture is we've actually grown the trees to be a little bit taller to where they are. And then they use computer modeling to do a 3D analysis rather than, I guess something more analog. It used to be that you get up on the rooftop with this device called a solar pathfinder, and you would walk the entire rooftop. And what this does is you have along the x-axis,